Okay, well, let's make a start. First of all, thank you all for joining this this seminar, part of our seminar series under the network TAPAS, Tackling Air Pollution at School. My name is Paul Linden. I'm based in Cambridge and the PI on this project. And we have a series of seminars on Thursday at this time, so welcome to that. The usual housekeeping rules is that this seminar will be recorded, so if you don't wish to be recorded, please don't keep yourself on mute and keep your camera off. Please put your questions to Mike, the speaker today, in the chat, and we'll deal with those at the end of his talk. Okay, so it's a pleasure to introduce Mike Bithell, who's in the Department of Geography at the University of Cambridge. Mike started off as a physicist, astrophysicist, working in the Rutherford Atherton laboratory, and then decided to come down a bit and study the atmosphere. And he moved to the geography department in Oxford before seeing the light and coming to Cambridge. He's now does a lot of extensive work with agent-based modeling, which he's going to talk about today, to investigate various problems in the environment and human interactions, including things like scree formation, climate, flooding, subsistence farming, infectious disease, and more recently, vehicle-generated pollution. And the title of his talk today is Agent-Based Modeling and its Application in Relation to Improving Air Quality in School. So I'm going to hand over to you, Mike. Thanks very much.
Okay, thank you for that. I'm just realizing that I'm used to getting up and standing up and walking around when giving a presentation. So I'll try and stay in my chair rather than leaping up and pacing up and down as I would usually do. The idea of this presentation is to just illustrate for you a technique for trying to model human behavior and give us some understanding of what the consequences might be of the way people interact with each other and with the environment. And this tool is called agent-based modeling. The agent there refers to anything that has agency, so anything that can make changes, that can change the state of the world or interact with other people or other things. And then to make that concrete, I'll just show you a case study where we built a model of a primary school. That will be about infectious disease, and that's largely because at the moment we don't have at that scale any existing models that have pollution directly as their target. So I'll talk a little bit at the end about where the state of the art is with this kind of modeling technique as applied to that sort of pollution problem. So just to introduce agent-based models as an idea, social systems are complex dynamical systems. So they're sensitive to small changes, they are history and dependent, so it matters what happens in the past. They can have sudden changes and tipping points, and different scales are coupled together through various different feedback mechanisms. And the way that the social systems work at large scale depends both upon the microscale, so individual people, what their beliefs are, how they behave, what decisions they make, but also on macro scale phenomena, so culture and politics, large scale structural inequalities, both in the built environment and in social systems, and what happens in the environment. So these things feed from each other, the large and the small scales, and a range of intermediate scales in between. And typically we don't have, as we do for things like fluid flow, any useful equations of motion for the dynamics of these kinds of systems. So instead we tend to rely on what we do know, which is that there are individuals, and where we think we can test some kinds of rules of individual behavior, we can then build a model around that and try to see how things scale up when we model the interactions of large numbers of these agents. And one of the advantages of this is not only it's a very flexible technique, as I'll show, but also that it can be something that allows people to get really to grips with the modeling process in a way that allows them to see things which they're familiar with every day. So individual people or houses or neighborhoods, things that they relate to, rather than a large scale kind of aggregate density based simulations, which might be a little bit more difficult for ordinary people to relate to their everyday experience. So there are a wide variety of agent-based models. They could be individual trees, animals, people, or larger scale things like households, vehicles, and that's not just autonomous vehicles, but vehicles that represent driving behavior when driven by humans, or organizations. So that there is one agent-based model that represents all of the companies in the United States, or agents can be governments, or cities, or even countries. Anything for which we think we can define some sort of rules of behavior and then try to see how those rules play out over time. And you can have lots of different types of agents present in a single model. So you can have companies and governments and vehicles and people and animals all in the same model. And what we hope is that when we put in these rules for individual behavior, that will get large-scale emergent societal properties that we can compare with things we can measure at societal scale and see how feedbacks between those large and small scales lead to change over time. Unfortunately, however, we don't really understand in any meaningful way how people make decisions, so we have to use some kinds of approximations to what individuals do. So the large square here represents the internal structure of an agent. So they might have some representation of a physiology, a perception of their own physiology and of the external environment and the hazards and resources that provides. And then from those perceptions, we might have a simple rule that goes straight to action, so-called reactive agents. Very simplistic, but those actions then impinge upon other things happening in the environment and other agents, and that gives us some kind of complex dynamics where we can test what happens with simple rules. The other end of the scale is you might have some very complex internal cognitive model inside the agent where it has certain beliefs, it can have desires and goals that it wants to meet, make those into intentions for action, formulate a plan, and then try to make the actions dictated by that plan effect change in the world, and then that feeds back again into their perceptions and possibly through the environment and their physiology. Most of the time, most models to date don't have this really complex internal cognitive states because it's very computationally expensive. And the model I'll show shortly is more like this reactive one, where you have just a set of prescribed rules and you try to see what kind of outcomes those rules will lead to. And the kind of places where it can be useful to use this sort of model rather than some other kind of modeling framework is, for example, where you need to avoid assuming that individuals are like the average. So someone with asthma, for example, has a very different experience of air pollution from someone that has better general health. And you may need to take that into account in the modeling process. All cases where individual behaviors are important and where they may change outcomes. So we've seen with COVID, for example, that how people behave affects strongly the spread of the disease, and non-compliance may change the way in which that happens. And that can be a function of age group or social conditions. The other cases where feedbacks between behavior and the environment are significant. The largest scale thing that you might think of in this context would be climate change, but it also applies to things like behavior. So you can imagine if drivers became sensitive to the pollution they were emitting, they might try to change the routes they drive to avoid polluted air, but that would then feed back into the traffic density, and where queues form, that would change the pollution field And those feedbacks could lead to some kind of unstable behavior in the distribution of pollution. The other thing we can do is to try to disentangle the effects of things like movement and other parameters. So for disease, it's really important to know what the transmission rate is, but that's a convolution of the individual person-to-person exact sort of physiology of disease and where people go, what they do, how long they spend in the company of other people. And those two things together, for example, create the R number, which says how many people infect other people. So it's you can parameterize your model to try and split those kind of effects apart. Other possible uses are where you have scenarios that you want to look at. So perhaps there's going to be a new road built and you want to know what effect that will have on the traffic flow and how that will affect the pollution field. You don't have any historical data that helps you to understand what that will do to things like traffic jams, but you can simulate that with an agent-based model. And other things, you might have a very complex, heterogeneous, different agents all acting together with conflicting goals and views of the system. So you might have a school or the local council and central government and parents and teachers, all with different views of how things should be handled and different ways of trying to understand the system. And with this kind of simulation technique, you can include all of those conflicting agents and try to understand how that might play out in practice. And finally, as I mentioned, you can make quite nice visualizations that are quite accessible using this sort of technique. More generally, you can try and test scenarios and look for unintended consequences where doing experiments on real people might be impractical or possible have ethical problems. So let me just try and make that a bit more concrete by looking at a model in a primary school. So this is a small school, it's got about 100 children in it. It's made it quite easy to observe the behavior, and it's a nice closed system, so there's little in and out activity during the day and very limited prescribed behavior controlled by the teachers and a schedule of activities. So it means we can make a model without having to account for too many different possible types of behavior. And I'll just go through what kind of data we had available and what the place looks like, and say a few words about the construction of the model before showing you a little movie of it running in practice, and then mention some of the things that are missing from it that might help to improve the model. So in terms of infectious diseases, as you know, infectious diseases can be transmitted by direct contact, breathing on people, or else by surface contamination. In this case, we're just going to look at a kind of proximity-based idea. So if you're close enough to another agent, then there's a probability per unit time that you will become infected. And then what drives whether you are close enough is the behaviors throughout the day, the places that the agents go, and the people with whom they interact. And here's an example of some of the data from 5 years worth of absences from school for medical reasons. So 2 outbreaks of disease. And what we were interested in here, and this model was made a few years ago now, was the kind of everyday illnesses that children get all the time. They just get sick and they have to go home. So not looking at large-scale epidemics, not looking at things like influenza, where the schools themselves form reservoirs for disease, and also not looking at COVID, because it seems like schools for COVID have not been really that important in transmission, except possibly as ways for bringing parents into close contact with each other. So here are 2 generic diseases, not really clear what they were. They caused a lot of children to get sick. The one on the left, you can see that there was some kind of propagation of disease from class to class. So in red, class 2 mostly got sick first, and then 2 of the other classes got ill, and then finally class 4 got sick at the end, giving a kind of double peaked appearance to the overall total number of absences, whereas on the right, some sort of disease ripped through the whole school population altogether, and all of the classes got sick at the same time. So the individual diseases can have different characteristics in terms of how they play out as epidemics. Let's look a bit more detail at the place. So we had a new toy, we had a laser scanner, we thought we'd take it out and do some scanning with it. So we took it and scanned the entire school inside and out. What you see here is not a photograph, it's a point cloud of all the laser reflections from somewhere outside the school. But where you can see on the left there, a sort of blue area, there you're actually looking through the wall into the classroom behind, because we can cut out sections of the laser scan and look transparently through the whole of the school. Or we can choose a viewpoint somewhere up above the ceiling and look down on the interior. And here you can see all the desks and the chairs and the computers. And we can see all of the individual pens and pencils. So the scan resolution is about 5 centimeters. So we've got a very rich data set of all of the things that were in the school at the time. However, ultimately, this was too much stuff to actually put into a model. So we simplified this enormously by just taking the ground plan, cleaning up those. So that was the laser scan points. This is that cleaned up into a line drawing, and then we zoomed in even further down to just the ground plan of the school, which probably we could have got from by other means, but at least we know we had that accurate to 5 centimeters. And then that was simplified further to this set of walls here in purple, and desks you can see in green, and the school playground on the left there in grey. So I'll come back to this picture as I go through the rest of how the model was constructed. As far as events go, we imagine that there's a virtual school bell. That school bell signals to teachers with a virtual timetable that events are about to, they need to change activities, and they then communicate those to the virtual children. And the teachers can vary these schedules by inserting or removing events or changing their timing. Children can attempt to do that, or they may not succeed in doing so. But once they're outside the classroom in the playground, they have free movement. So we break things down like this. And one of the points about this is we try to use the individual and fairly exact timings down to 1 second resolution, so that we can resolve all of the movements of all of the children properly, and whether they're about to collide with each other or with walls and so on. Many agent-based models just use a virtual time that isn't related to anything realistic, but in this case, since we're trying to match this back to the disease data, we needed to try to make sure that all of our timings were correct and lined up with the school day. And then the teachers can take an event like going into school, and they're able to introduce a variation of the timing of that. So when children line up in the playground, as you see in a moment, they don't all go into school at once, but they file in some order determined by the teachers. And similarly, during lessons, each teacher has an individual virtual lesson plan where they can schedule different activities and cause the children to move around within the classroom during lessons. So we take that location and those virtual timetables and bring those into this ground plan as I showed you earlier. The background grid, which I hope you can see there, is 1 meter scale. So that's roughly the size, the resolution. And the walls and the desks are obstacles to agent movement, but so also are the other agents. This is just a labeling of the classes. So you can see the 4 classrooms with the desk in, and the hall where children have lunch and go for assembly, and then playground on the left, as I said earlier. So we implement the barriers to movement using what's called a social force model. So we imagine there's some kind of virtual repulsive force between agents and walls and desks, but also between agents and each other. That force gets larger as they get closer together. And that's something that's been used for pedestrian simulation and reproduces some of the things you see, such as lane formation on crowded pavements or intermittent going through doorways where there are people from opposite directions trying to get through doors. So it means that the children kind of push each other around and jostle in a relatively realistic manner. And with the red dot there, you can see one of the agents that's going to be a seed point for the infection that'll go through the school. The other thing we have to have is some kind of knowledge embedded in the agents of where things are. So they know, for example, where doorways are, and they also have pathways that they have to follow when going from one location to another. So here you can see a crocodile of children going through the hall. They could in principle go through this corridor that's above them in the picture, but that's not actually allowed by school rules. So they have to file through the hallway and out again in order to get to their classroom on the other side. And those pathways are prescribed ahead of time. You can have agents kind of work those pathways out for themselves, but again, that's computationally more intensive to do, but that would be what you would do for a traffic model, for example. So those would have route finding algorithms built in. So let me just see if I can show you a version of this model running. I hope you can see this. So this is the start of the day. It's just before 9 o'clock, and I hope you can see these little things moving in here. These are the children coming into the playground and milling around. One of them has come in with an infection, and you can see they've already infected another child. So this is for the purposes of illustration. This is a much more virulent and rapid spreading disease than anything you would get in practice. So now they've all lined up, ready to go into school, and the teacher heads off into the classroom, and the class will follow them through into the various classrooms. 3 of the children have now got the disease. And after they've moved into the classrooms, obviously this will just spread within the class to individual children that are close enough by. There isn't any airflow or anything like that in this model, so the disease will only spread if you're actually within some finite distance of another child. And that varies obviously throughout the day. So around about 9:10, after they've been into the classroom, the children all go into assembly in the hall, and there's another opportunity for them to pass the disease on to other children. There are some other simplifications here. For example, the issue of going to toilets is not included, which could be an important point for spread of disease by contact. And things like children putting down all of their coats and hanging their coats up and putting their bags down, and those kinds of things are not included. So hopefully you can now see them all moving into assembly. So they go into that one class at a time and all line up at their places there. And this disease has now spread to a very large, a reasonably large fraction of the pupils in just 10 minutes. So not particularly realistic in this particular case. And this is one of those cases where everybody in the school will get sick at once. So having this very high transmission rate for the disease is the kind of situation in which you'd expect there to be an epidemic, where all of the classes are all going to get sick together. So they spend some time in assembly, and then try to skip forward a bit. You can see the disease is now spread almost all of this one class and spreading to the rest of them. And then they'll file out from assembly again after a realistic length of time spent in that location, and go to do their activities in the classroom. So I go back to presentation now. So here's a comparison of some of the data with a simulated disease. So the data on the left and a simulated disease outbreak on the right. And you can see that we're able to reproduce this kind of class to class type of propagation where one class in red here, class 2 in the simulation, then spreads the disease later to class 3. So we can capture some of the properties of these diseases, and then by calibrating the model so that it reproduces the data, we can infer, for example, what the transmissibility of this disease would be at the individual person-to-person level, assuming that we've got the range of transmission correct. And we can do other things like look at the places where the children acquired the infection, and that might allow us, for example, to pick out places or policies that could be changed in order to reduce transmission. In this particular case, it seems like it's just random everywhere. So apart from the playground, there isn't really anything obvious that could be done here. It's not like this disease is spreading only in the hall or only in classrooms. It seems to happen even in transit between the hall and classes. But there are some things that this model doesn't include and doesn't get right. So here's an example of where it doesn't do so well. So the heavy line here is the number of days absent in the model, and the light line is consecutive days absent in the data. And you can see that we fail to capture the a big peak in absences of about 1 day. And that's largely because we don't have any kind of stay-at-home rules for children that have become sick, or any prevention of sick children from going back to school until they get better again. So there are things we could add to the model that would help us to capture this kind of effect better. And other things that are missing, we don't have any social networks, so there are no friends. So in the playground, the children would tend to cluster and spend time with friends, but they don't do that in this model at the moment, and they just mill around, and that may be why we get very low transmissibility in the playground. There are no parents or support staff. We don't have any precautionary absences when children seem to be sick. There's no social distancing. There's no adaptation of the school regime for large outbreaks. There's no seasonality or airflow or any of these things. So many things that could be added to this model that would help to make it more realistic. So that's really all I wanted to show you in terms of this disease model. Just some acknowledgements there for people who helped with the data collection. In terms of public health, by and large, almost all of the models to date, agent-based models of any scale or any type, have focused pretty much exclusively on infectious disease. There are a few examples looking a bit at vector-borne disease, some public health issues such as eating and access to food, things like food deserts or places where access to fast food is very prevalent have been looked at, and models have been applied to exercise, but almost nothing right down at this kind of fine-grained school scale as yet for pollution. So there are traffic models which are reasonably well developed. Those can operate up to city scale with several millions of cars in. Some of them do also generate pollution, so that will typically be simulated more at the kind of scale of a city block. And there are models that will incorporate some sort of realistic diffusion of the pollution or fluid flow together with an assembly of cars of different types with different pollution generation. But those by and large have not really then been used to look at exposure. On the other hand, there have been a handful of studies, 2 or 3, that have looked at both traffic and pollution together with exposure to pollution above some threshold level, largely as proof of concept models, and generally at relatively large scale and very coarse resolution. So we made a model relatively recently that looked as a central business district with two types of agents, so commuters that would have to walk to work on foot, and people commuting in cars, taking into account some fairly crude degree of ratios of indoor to outdoor pollution during the day, and focused mainly on pollution generation above background from tyre wear and braking, so non-exhaust emissions, and tried to estimate what the exposure of people would be in their routine daily activities to pollution events above, for particulates above. Well, in the particular case, we were looking at 100 micrograms per cubic meter, so fairly high levels. Work was done in Seoul, and another model in Beijing looking at how pollution levels might change with a switch from conventional cars to electric vehicles, but nothing really that gets down as yet to this sort of fine scale school level model. And a lot of the outcomes of these kinds of models are quite sensitive to behavior. It's not really clear how to go from that exposure to health effects. That's quite a tricky problem. The pollution generation interacts with things like airflow and weather, and that's not an effect that has widely been included along with this kind of agent-based modeling. So there's a lot of progress that could be made, many areas in which this kind of model could be developed. And I hope that's given you kind of a flavour for the sort of thing that we might be able to do in the future. And I'll leave it there. Thank you for listening.
Thanks very much, Mike. I'm not sure if we have Paul. Paul, I think he may have perhaps become disconnected. Paul, are you there?
Yeah, sorry, I'm here. Yeah. Yeah, thank you, Mike. That was really interesting. And please do. Oh, sorry, I seem to be muted as well. Yeah, please put questions in the chat to Mike. I'd like to start off with one. You went to the beginning with lots of precision, measuring things down to incredible small spatial scales, 5 centimeters, I seem to recall. And yet, in the end, it doesn't seem that's particularly relevant. I mean, why did you need to do that in the first place?
I think it's called being overambitious. In principle, you might imagine that there could be critical parts of the process that depend precisely on where things are in the room. So where are the resources kept? Do the children have to all go to the corner to wash their hands at the sink after they've done painting? Do they have to go to the stationery cupboard to fetch pencils and that kind of stuff and then come back again? And how would that affect the contact time for a disease that's very small scale? Where might a surface deposition happen? If they're using computers, should we include that as a location where it's more likely that children are going to lead sticky fingers that could transmit infections? So you can imagine all kinds of things that you might want the data on that it would be difficult to go back and fetch later. Since we could gather the data, and it wasn't an extra effort to do this. I mean, it only took us a day or two to do the scanning. We thought we'd go for high detail and then see where that took us with the modeling. But in practice, developing the model was sufficiently hard that simplifying everything down was what we ended up with in practice. So Yeah, and you know, it was quite nice to make this kind of laser scan model of the school. It's kind of a nice thing to do.
Yeah. So I have a couple of questions in the chat now, which I'll start with. So Wazim Jabi says, what level of accuracy of these models is usually expected and considered acceptable? What is usually measured?
So that's, you know, that's problem dependent. So if you're thinking about level of accuracy, for in this case, what we wanted was to be able to have time resolved data on the disease transmission. So I wanted to be able to make sure that we had that sufficiently finally resolved. And therefore we wanted the positions of the children down to individual kind of meter scale resolution, so that we could say, well, this child is close enough to get the infection from another one that's next to them, but not from one maybe on the other side of the classroom or on the other side of the desk. So the driver for that is basically the data that we have to compare with at the end, which is the epidemic data, the school absences. If you're thinking about the accuracy in terms of where children go when they're walking from one classroom to another, well, that's not going to be fantastically important for most kinds of things that you're interested in, except for the fact that you don't want children to pass through each other when they're walking along the corridor. So you need a sufficiently good time and space resolution to be able to make sure that when they crowd together, they form a crowd and they don't all kind of end up stuck on top of each other. But you wouldn't expect to be able to recover, other than in some kind of statistically average sense, the trajectory of a child through the day. You're not talking about literally modeling individuals. You're modeling representative types of individual that are a bit like a real child. But the output accuracy, what you measure, entirely problem dependent. What do you want to know is the question.
Right. I mean, so in that example where you take proximity as a measure of the risk of infection, then you're kind of making an assumption about how the disease spreads, right? Which may or may not be the case, I suppose. That's one of the issues that you can test, I suppose, as a result.
Yes, so you could change the radius of infection. You could change it into a kind of a mixing model where you have some kind of density of disease particles in a room, and then the children get the disease depending on whether they meet a dense patch of kind of airborne particles. This is the simplest possible starting point, is just to say, well, it's how close you are. But you can make that more complicated depending on whether you have useful data about that. So yes, it's a testable assumption.
A question from Sophie. She asked, can you combine these agent-based models with the type of large eddy simulation models like fluidity that we use in MAGIC?
Well, that would be a nice thing to do. I don't know how easy it would be. Model coupling can be challenging. And it would depend at what level you wanted to try to make that coupling work. Do you want to just have the fluid simulation provide you with a background field and then the children move through that but they don't perturb it? Or do you want to actually fully couple it with child movement so that if they run across the room they actually change the airflow, or they are a source of emission of particles in the case of a disease that causes changes in the density of disease particles? But yes, in principle, but you'd have to think again about what you're going to get from that. So if you imagine you've got I don't know, PM 2.5 coming in from outside, and you've got an open window and you can simulate the flow of those particles into the room and that airflow is just passive and it's not perturbed by the children as they walk through it, then you could imagine using this type of model to say when they encountered that plume of particulate laden air as they moved around in the classroom, and see whether that was important. It might be that, you know, actually it's good enough to use some kind of averaged density of particles and an averaged position. So it allows you to test really whether doing things at this kind of micro scale is something that you need, or whether you can get away with something more simple and less computationally expensive.
Yeah, we have Hugh on the call. I don't know whether Hugh Woodward, whether you want to comment on that, whether you, because you've been looking at exposure.
Yeah, I admit I wasn't listening. So
Sorry, Hugh.
I was half listening and half working at the same time. So the question, you're talking about using fluidity coupled with a kind of modelling that Mike just present. Yeah, I think my first reaction to the question was that, I think Mike sort of touched on it, but that it's so complex to do. My thinking with modelling like this is I guess I'm repeating what you said, so I guess I was listening to some extent. It's to test whether it's necessary, right, or if is it overkill. So the question is always there. So, you know, is the well-mixed assumption good enough? Well, how do you work out if that's the case? Well, you use a more sophisticated model, even if it's a completely made-up scenario, and you see if it makes a difference and what kind of difference it makes, right? But I think, yeah, I don't know what the actual answer would be. It's such a complicated thing. The problem with this thing as well is it can make a difference for one-off occasions, but then if you're modeling on a population scale and you're trying to get an idea of the R number, for example, often these sort of fluctuations average out and you end up with something similar to what the well-mixed model would have given you in the first place. So it sort of depends on the timescales as well. So I think it's a very difficult question.
Right.
Thanks for dropping me in.
Yeah.
Yeah, there is some evidence that for diseases it depends on the scale. So if you have a large outbreak with a very large number of people in it, then you can probably get away with using an averaged large scale compartmental model. But if it's a small disease outbreak, then the individual behaviors may become important. And the ditto with mask wearing or that kind of thing.
Yeah, exactly. It's that difference between individual risk and population scale. And they're both equally valid questions, right? You want to know, on an individual level, you want to know if, for example, you keep your distance from other people on a train, that will reduce your risk or not. But then resolving that spatial distribution within the carriage, I'm using trains as an example because that's what I've concentrated on, might not be relevant on a population scale. That doesn't make a difference, right? You can use well mixed. So it really depends on what question you're asking.
Yeah. Well, thank you. I didn't mean to drop you in it.
No, it's fine. Don't worry.
You recovered.
I should have been listening.
Yeah. So there are no more questions in the chat, unless anybody would like to raise them now. Very welcome to do so. Well, if not, I think it just remains for me to thank Mike for a very interesting talk. I think these approaches are really interesting in the sense that, as we just discussed about the idea of proximity and infectivity, it allows you to test things, I think, which are really quite hard to test in other contexts, and particularly when you can compare them with data, as you did for school absences and so on. So I think it's a very promising area, and so thank you for telling us about it, Mike. It was a very interesting talk. And I'm afraid we can't give you the usual round of applause, but perhaps I will do that anyway. And thank you. Just to say that next week we're having Corinne Mandin from the Scientific and Technical Centre for Building talk on indoor air quality in schools, from knowledge to actions. And Sophie's actually put the details of that in the chat. And so those of you, I hope many of you will join us again next week. And for those of you who are here today, thank you very much for attending, and look forward to seeing all of you next week. In the meantime, have a good week. Bye-bye.